The single cell core will give you one cell ranger output per sample or one Seurat object per sample. And with each sample individually, you will go through the entire pipeline. So you will run scatter on each sample individually because different samples can have different issues. And with each sample, you will also go through the entire Seurat pipeline. So you will get one Seurat object per sample, and then you are going to merge them into one combined Seurat object using the merge function from the Seurat package. So to merge two Seurat objects, you are going to use the merge function. So this here is the first Seurat object, and the Y argument is the second Seurat object. You can merge more than two Seurat objects. In that case, the Y argument will be a vector containing multiple Seurat objects. What is important here is also this argument adds cell IDs. So what you write here is an ID for every sample, for every Seurat object that you are going to merge. So when you merge two Seurat objects, the value of this argument will be a vector with two IDs. When you merge three Seurat objects, the value of this argument will be a vector with three IDs. So one ID per sample. He's going to put all the cells from these three Seurat objects in one big Seurat object, but that means that you need to have a way to recognize which cells come from which sample, and that's what these cell IDs do here. You see that when you look at the cells after the merge, the barcodes will be preceded by the ID that you write here. So all the cells from the first Seurat object will have a barcode that is preceded with the word 3K. And all the cells from the last Seurat object will have a barcode that is preceded by the word 8K. And this is how you can recognize which cell comes from which sample. When you have a Seurat object with combined samples, you go through the entire Seurat pipeline again. So through the entire pipeline, starting from the normalization up to the clustering and the UMAP. So you will produce a UMAP, and on the UMAP you will color the cells according to the sample they come from. And this will allow you to check whether you see any batch effects. How do you see batch effects? Well, either the different samples are shifted compared to each other, or, as is the case in this example, clusters consist solely of cells coming from one sample, and this is not a good thing. So if you see a shift between the samples, or you see the fact that the clustering is driven by the different samples, you have to think about the fact whether it is possible that you have a batch effect in your data. So where do batch effects originate from? Well, for instance, you retrieve a number of samples in week 1, and then in week 5 you're going to retrieve another set of samples, and then you're going to combine them. This will inevitably lead to batch effects. Or you retrieve a number of samples and your colleague retrieves another set of samples, you combine the samples, again you will see a batch effect. Or some of the samples were sequenced in one lane on the flow cell, other samples were sequenced in another lane on the flow cell. This will lead to batch effects. So you always have to think about, is it possible that I see batch effects in my data? If there's no reason to expect batch effects, you don't have to correct for it. Even if you see small differences here, the differences will be very likely biological, so you don't want to correct for them. However, when you do expect batch effects and you see on the UMAP that the samples are behaving differently, in that case you have to do a batch correction. For batch correction, you use the function integrate layers from the Seurat package, and it provides multiple methods for doing a batch correction, going from very harsh methods that you use for very strong batch effects to less harsh methods that you use for smaller batch effects. Now, there needs to be a bit of nuance here because the single cell VI, I listed it here as the least harsh batch correction, and it can be the least harsh batch correction, but basically it is as harsh as necessary. So you can also use single cell VI to tackle very strong batch effects. It will also work. It adapts the stringency according to the severity of the batch effect. So how strong is the batch effect that you expect? Well, it depends on the source of the batches. So when it's simple replicates, you don't expect to see a big batch effect at all. However, when you're going to combine data from different species, you do expect to see a very strong batch effect. So you need to adjust the correction method according to the source of the batch effect in your data. For very strong batch effects, you will typically use the Seurat method. For very small batch effects, you use one of the less harsh methods. Please note that methods that are very harsh, that can remove very strong batch effects, they also tend to remove biological signals. So you will also lose some biology if you do a very harsh batch correction. So if you expect batch effects in your data and you don't see a batch effect in your UMAP, then don't do a batch correction. If it's not necessary, don't do it, because a batch correction will always remove some biology in your data. So in a small data set, with a very strong batch effect, the CCA method from Seurat and the RPCA method from Seurat are considered the best choices. In a large data set with strong batch effects, single cell VI will produce the best results. It will remove the batch effect while removing as few biological signals as possible.